very happy to be here. Thank you, the organizers, for the invitation. The Sensei, I think you say, the actor, sorry if the name is not right, actor that I meet frequently in conferences. Also nice to see Malte is here, Bla is here. Then, wow, that's so awesome. I'm happy to be here. Wish we could be together having a beer, but anyhow, it's happy to be here today online. And I'll have later today on behalf of the event, or in honor of the event. I'm Elias. I'm a professor in the Causal AI lab and in the computer science department at Columbia University. I'm usually on Twitter. If you are there, follow me. And usually if you are interested in things related to causality, reinforcement learning, AI, and so on, I usually exchange ideas there. As mentioned, this is a kind of short version of the talk. The first time that a short version of the tutorial that I presented last year at SML, that was maybe three hours or 3 to 4 hours tutorial. Check it if you are interested as well, the crl.causalai.net. Perhaps a suggestion for the organizer for the next year, maybe you can organize a tutorial in Causal RL at the conference. I think it would be good. Then anyhow, today I'm talking about the towards causal reinforcement learning. That is kind of my reflections about the relationship between causal inference and reinforcement learning. In particular, I will give you a kind of idea about the problem of generalized policy learning. That is one of the problems that we are starting to chart or to map in this general CRL landscape. I'll be interested in hearing your thoughts. I will start doing just a kind of 20,000 view what's going on in the causal AI landscape to see where we are situated. And kind of the premise here and what's happened in my lab or in my research in the last 10 years or so. The main idea observation starting from the PRL is that any system usually runs this collection of causal mechanisms that he defined as a structural causal model. Now, the inferential tasks that we are interested, I classify as in 2 buckets. But usually this collection of mechanisms, we never observe them. This is kind of laws of nature, except in very special cases, such as maybe physics or chemistry. In some cases that we are kind of getting the laws of nature in a very precise way, usually you don't observe the structural causal model. I call SCM from now on for simplicity. But they're still there. It is running the code of reality in some way. Now, one kind of side of what we are trying to do is to explain how nature works or how this reality works. Then there is this new bucket here that we call explanation or explainability that in causal inference has many different tasks, including effect identification and decomposition, bias analysis and fairness, robustness, generalizability, transportability, and so on. And this is one of the buckets or the kind of tasks. But there are many maybe books now written about that. This is what means maybe to do science, try to explain how things work. The important take here that will make a lot of differences about this is coming from this structural causal model or this collection of mechanisms that give semantics to the quantities that we're trying to infer. On the other side of the reality, in another bucket, we have, maybe you can say, Elias, I couldn't care less about explaining something or how things work. I'm a pragmatist. I just want to improve the bottom line, and maybe I don't want to have COVID to society, or I want to improve the well-being, or I want people to have better education, or so on. Maybe I have some sort of targets that I want, or I want to improve the bottom line of my company. If you're a company, then maybe you don't care about explaining. At least your goal is to decide and trying to improve something. It could be possible, or is a valid goal. Different names comes here. The one used in machine learning is reinforcement learning. There is in the fields of medicine or biostatistics, there is randomized controlled trials. That's a variation of that. Now you also have personalized decision making and so on. For sure, there is some kind of interaction between them. In principle, they could be studied separately, but if you understand more about the system, at least in terms of expectation, it will be that you can do more, you can make more surgical interventions and decide better. On the other hand, even if you don't understand a lot, but if I'm just kind of perturbing the system and intervene, this could lead to better explanation or better understanding I should say, of the system. But at least in my lab, each paper kind of falls in the bucket. This kind of interaction is still very not well studied. I cannot cite one paper in the literature that is that I think that is nice in this sense, and there are reasons for that. But anyhow, at least as humans, we can understand, and we use this kind of loop in our own decision making, understanding, and operation in the world. Anyhow, this is the theory. In practice, we can have applications, educational software. We are interested in the lab. Two types of application kind of pops up. First one is the data science. That is, we would like to be principal and get this label that we are being scientific. Then we like to have principal inferences from large data collections for explaining or for deciding. On the other hand, here we could have something called AI/ML, that we are trying to learn principles and tools for designing robust and adaptable systems. Now, today I'll be talking in particular of the branches here on the reinforcement learning and applications, or the idea applications in AI. Then what is the what I have been calling, or we have been calling Causal RL. Reinforcement learning usually is pretty good from a high-level perspective. It's pretty good in handling sample complexity and the credit assignment problem. Causal inference, and I'll talk more about each one of them. Causal inference is quite great in leveraging data and the structural invariances that are across settings, conditions, and environments. Then this is kind of the purpose of causal inference in some way if you go to the foundation, how to leverage the invariances that are in the environment. Now, the question, can we have the best of both worlds? This is optimistic you're discussing before the talk. As optimistic view, yes, and I think it's true. And the solution is kind of, let's try to combine them. I think, as I mentioned earlier, maybe 3 minutes ago, there is this, I'm calling that the CRL. There is kind of 3 plus hours tutorial that I recommend if you are interested. I will just try to give a very brief summary about what I believe is going on, crl.causalrl.net. Our goal in general will be to provide a cohesive framework that takes advantage of the capabilities of both families from first principles, of course, and allows us to develop the next generation of AI. Then what does, this is kind of textbook picture or RL. What's the difference between RL and CRL? This is kind of common question here that's kind of preempting or valid question. This is textbook picture of RL, in which you have the agent that is essentially a collection of parameters, whatever language you want to parameterize that, you can call theta. You have an environment on the other side. The agent perceives the environment in some way, then decides run something, decides to take action in the environment or make an action, and then receives a reward. Then this is the general idea here is trying to maximize some version of maximizing the expected rewards. Now I was trying to summarize and see what's the one step delta, smallest delta, how can I explain what we are doing in the CRL. And this is the picture that I have. I think it summarizes everything that I'll say. Is like, instead now about talking about a set of parameters abstractly about the environment and a set of parameters theta, we'll just add one thing. We will add the environment that will be modeled by a structural causal model following Perl's language for the code of reality, the M. Then there is an SCM M explicit there on the side. I don't have access, but this is the one that is evaluating whatever we are doing and the actions that we are taking. And on the agent side, there is a causal diagram or causal graph G. From the causal diagram, for sure, you have this induces a collection of parameters, but the causal diagram, there is some type of invariances that are encoded in this diagram. Now, for sure, the agent still obviously observes the environment, or there's a context or a state that it perceives. Then it takes an action. Action is a word that is overloaded here. There are different types of interactions that the agent could have. One is observing, that's just mentioned. The other is interventional. and the other is counterfactual. I'm not sure if you read, I forgot to add here the link, but check Yuda Sproul's The Book of Why. He has a very nice book called Book of Why. It's kind of popular, it's general summary of the area, but the main metaphor used in the book is something called the ladder of causation. I call the pearl-causal hierarchy, but he calls the ladder of causation, that is exactly about these different types of interactions or views that you could have about the environment. One is observation, that is called layer 1. The other is intervention, that is called layer 2. And the other is counterfactual, that's layer 3. Then we'll use as our baseline about the relationship between the environment and the agent. Then the two key observations that I said when we move from RL to the CRL, for number one, the environment and the agents are now tied through the pair SCM, M, in the environment side, and the causal graph or causal diagram G in the agent side. Number two, we'll define different types of actions or interactions between the agent and the environment through these observations, interventions, and counterfactuals. That's the summary. Everything else will follow from that. Now, decision-making problem, what we're trying to do now, I'll start just to, obviously everyone knows here, but I'll try to frame slightly going to use our notation. The learn a policy, our goal will be learn a policy that given an individual characteristic C or assertive context C, could be the state, selects the action do X is equal to small x, this is the intervention do, that maximizes the expected reward E of Y given do X and C. Sometimes I will omit the word E or P just to make it easy to speak. The applications are, I think people are familiar, medical domain that we're trying to decide patients based on the patient's information that we have, some kind of best treatment strategy, advertisement if you're a company or Google and so on, learn the product recommendation that maximize the satisfaction and the profits of the company. Now, summary of the views about different strategies that we could find in the literature. Those are three big buckets, not saying that is exhaustive, but it's the ones that I'm more familiar with. One is called online reinforcement learning that we are going to, anyhow, I will go one by one, but we are going essentially making the decision, taking the actions in a hardcore or a hardware-like way. And there is this last two here that is kind of more softer way, that is the off-policy learning, and what is called the causal inference, or I'm called the do calculus learning. Now, going one by one, reinforcement learning is a goal-oriented adaptive method that learns through interactions with the environment, external environment, and environment. It's online, which means that the optimal decision, the P probability of Y, given that you take the action do X, big X is equal to small x in the context C, is learned through the randomized experiment or adaptive strategies. If you have the UCB or Thompson sampling or any kind of strategy that you're changing along the way. The positive about this thing or this method is robust against unobserved confounders. This will be a big deal in causality, that we have these latent variables that we eventually do not observe, and is affecting the observed behavior. One of the main concerns sometimes I'll talk for short UCs, for unobserved confounders. The negative of this strategy is good for that in some sense. The negative for that is experiments can be unethical, can be expensive, or technically challenging. If I want to know the effect of just it's obvious, the first two is obvious about smoking and cancer. I cannot experiment with people. Expensive to run some of these trials. In this bucket, this costs maybe $5 or $10 million. And technically challenging, it means that perhaps I'm trying to get to the effect of cholesterol and heart failure. I cannot randomize or I cannot control the cholesterol. Then it's not, even if I have all money in the world, it's still not possible to control this variable. This is the online bucket. The offline bucket is the optimal decision Y do X C is learned through experiments, but conducted by other agents or different policies. Positive here is that no experiments need to be conducted. That's great, because we can save all this trouble that we have here. The negative is, or the possibly negative, is that rely on the assumptions that the data available is collected under the same context. The two agents observe the world in the same way, and the same interventions. They are randomizing or controlling the same variable X, and also the populations or environments also the same populations and environments are considered, which is quite strong assumption, at least in general. What about causal inference? Causal inference, optimal decision can be learned from a qualitative description on the environment, that is the causal graph G, and non-experimental data, also called observational data. The positive here is like the effect of general types of interventions can be computed even when the context is unknown and intervened variables do not match what was done in the original policy or by the other agent. In other words, the off-policy learning assumptions are violated. That's kind of where causal inference starts in some way. The negative is, or the possibly negative is like results are contingent on the model. Under weak models, in other words, if you have very low understanding of the system, the effects will be non-identifiable, as we call in causality. Should be not defined, but should be defined, or it can be formally defined, I should say. Now, here's one example of a setting. You are trying to make the action X. This is affected by a context or a state C. C affects X, the action decision. C affects Y. C in turn affect a mediator Z, and this variable Z would affect the variable in turn, the variable Y. But in this case, there is this UC, an observed confounder U, that is also generating variations or exogenous from outside, exogenous variations for X and Y. Then this could be a challenge. Causal inference could take this, if you use the causal calculus engine or causal calculus method. In reality, we're talking about the intervention, we call this policy that I said pi, that is taking the value C into account and making the decision, and is marginalizing or not taking into account the U. And so we given that is an observed. Then you can, maybe hard to see, but the challenge here is like you can go from a very challenging situation that is in the left, in which there is the variable U affecting X and Y, to a situation in which, given that we don't observe U, I can still talk about a policy pi C and try to evaluate this policy without going online. Without going online, just with the data from the agent collected in the left. That's the idea of the causal inference method. Now, different tasks that's the general picture, right? Different tasks related to this kind of big thing that I said, or this big task about decision-making. I will list some of them. This is in the website. One that I will talk today more is called generalized policy learning. That is about combining the online mode and the offline mode of learning. There is another task that's called when and where to intervene. The headline is refine the policy space, whatever this means, but the idea is like, we don't necessarily always want to intervene. Sometimes the system is already going to a good direction. And whenever you can prove results like that, sometimes we put our hands in the system and decide to perturb and you mess up the whole thing. It's very important to know when you should intervene, and if you should, because perhaps the situation is not good, where should we intervene? The assumptions that I should the usual assumption is that we should intervene in as many places as we can. It turns out that this is not the case. We have a sequence of papers showing that this is a bad idea. It's a task by itself and a learning opportunity, I would say. Challenges and learning opportunities. I'm listing here some. Number 3, this is a piece of work with Yuda himself, the counterfactual decision-making, optimization based on intentionality, free will, autonomy. I'm not talking about that, but it's quite interesting, starting in the RIPS with Pro 2015. Another task is about generalizability and robustness of causal claims. It's called the transportability theory. The other is like how to learn the causal models if you don't have one, discovering the causal structure with observations, combining observational, kind of the perception of the agents with the muscles of the agents, of the experiments, the interventions that the agents can do. And another one, this is more recent, that is from last year, that's called imitation learning, policy learning with unobserved keywords. You can show kind of quite stringent assumption about imitation learning is the whole endeavor in machine learning, can show how fragile it is and how things could break down if you don't take the causal structure in some way into account. And then we'll do that in the paper and show how we believe that at least the imitation learning should be done. I'll not go one by one here in these tasks for the sake of time. Today I'll be talking about generalized policy learning in particular, as I said. Now let's start online learning. Just again, the online learning tasks to make it clear. Online learning is usually undesirable due to ethical, financial, and technical constraints. In general, one wants to leverage data collected under different conditions to speed up learning. On the other hand, the can now see your screen. Are you guys able to see my screen? Because something popped up. Okay.
I see.
Okay.
Yes.
On the other hand, thanks. On the other hand, offline learning is usually too constrained. In practice, somewhat frequently, I should say, the required assumptions are violated. We can play a wishful thinking kind of pink world, but usually they are violated. Now I would like to try to be serious and move towards more challenging and realistic learning scenarios where these modalities, whenever these modalities are insufficient by itself, the online and the offline modes. Offline, including here of policy, RL, and do calculus learning. In this task, we combine them in a principle in what is called the generalized policy learning, GPL. Let me give you an example. Assume that we have the input is this, I just have observational data over these two variables, X and Y, and we are trying to learn the P of Y do X, the effect of X and Y. Y could be the reward that we're trying to compute. This is the causal graph here, and you have this unobserved variable U that is both affecting X and Y. This is what is called the natural regime. This is the control regime. When we are intervening, the variable agent is intervening in the variable X and picking the value, which means picking its values and arranging over the U here. If you try to apply, you have data collected over this regime, and I'm trying to speculate now or to compute or evaluate the effect on the right side here. If you try to apply the method that is used to do that, it is of policy learning, RL of policy, in reality, we will get that it's not possible to do it because there is a mismatch between the perception of the two agents. One agent in the observational natural regime is observing the variable X, while we don't observe variable U, sorry. While, in other words, U affects X, the decision X, while in our setting, U doesn't affect. We don't have access because U is unobserved for us. Then of policy is not an option for us. The number two, do calculus. If you try to apply do calculus, pros do calculus, but do calculus I would say, because from all of us, and this model, the theory you say is probably the case that you cannot compute this quantity from this data. Impossibility result. This is smallest impossibility result, by the way. Now, for sure, people could go online or consider go online. I will go online, but obviously we are trying to avoid that. That's the whole point that I'm saying here again and again. Because of the cost and this and so on. Now, if you, I'm looking for the easiest possible example to show the point. Let's go Thompson sampling in a basic setting just to show what's happening. Then I'll call the naive TS that is trying to use this observational data here, P of X and Y, as the prior distribution of this Y do X. That is what I'm trying to learn. And I will plot that. The x-axis is the number of interactions or trials, as we call. The cumulative regret is in the y-axis. There's just the oracle or optimal minus what we are doing. And this is the plot that we get, the line that we get. I would like to contrast that against what I'm calling traditional Thompson sampling, that's essentially throwing away this data here. Then this is really the online learning mode. And this is what we get. The blue line here is the one discarding, which is kind of the usual behavior. If you get the ziggurat bounds or whatever you kind of get, or the basic behavior that we expect to be something like that. In the beginning, there is some kind of learning. After you learn, things stabilize, and we know how to make the decision. It's kind of textbook picture here. Now, what is not textbook, what is hard for us here to swallow is like, how come having more data in reality is hurting us? Because how is it possible the data from this guy, if I use as the prior for this one, we are getting killed? Which seems to go against this strong intuition that the more data should help. And I should be able to learn from other agents despite the fact I'm not exchangeable, I'm not exactly the same of the others. No two agents are created equal. If someone like some code, this is another one. No two agents are created equal. This is obvious. Well, even when they evolve a little bit later, they are no longer the same. Anyhow, now let's open up. Let's try to open the plot that I just showed here and see what's happening and seeing the now. Let's try to parse slowly here. There are different moving parts. First one, these two lines here are you can see my lines, right? I assume so. Oh, my mouse, sorry. If so, if not, please scream. If you can, I'll keep moving. But these two lines here are saying this is the ground truth that you don't observe. The solid one is the do x0, and the dashed one is the do x1. It seems that the dash do x1 is below do x0. Then do x0 leads to a higher reward than the do x1. Now, it turns out that in the data, in the lab, the non-experimental data, if you don't understand Thompson's assembly, it's just, sorry, I just said here. If you don't understand Thompson's assembly, it's just allocation algorithm. It's just how you're picking the actions based on some kind of probability, and there's some kind of Bayesian interpretation for that in a very short way. Please don't kill me here if you are the Thompson sampling person. It's a Bayesian way of doing allocation of decisions in general. I can elaborate in the Q&A if that's an issue, or I can take it offline, it's better. And apologies for doing a little bit fast here, possibly. But anyhow, from the data, we can see that E of y given x1 is this one here now, is greater than E of y given x0. And that's observation from the data that is non-experimental. However, from these lines here, we are saying that the opposite is happening. The y given do x0 is greater than the y given do x1. And it's flipped. And no matter how many interactions we have, we are unable to flip the behavior of our allocation decision procedure. On the bottom plot, we have a traditional that throw away the data, and here you have a 50-50, and after around maybe 500 interactions, even less, and by the way, the shaded here is the uncertainty of the algorithm, because this is kind of a probabilistic thing. After around 500 or less, we already have completely disjoint decisions, and you already can catch that the do x0 is better than the do x1, throwing away the data. Now, the question for us is like, why the naive Thompson sample behavior is so bad, or so pathologically bad? We'd like to try to explain that, and this gives, in reality, is the problem of non-identifiability. Let me try to give you an idea. Not fully parsing here, just want to give you the map of how I think about that, and we can parse later all the details. This is I told you in the beginning, you have the pair, right? From the agent side, you have the causal diagram. From the environmental side that we don't have access to, but it exists, this collection of causal mechanisms, or the SCM-M. The SCM is composed of two components. One component, a distribution over the exogenous, the latent variables U, that is this one, and also has a collection of functions for the observables. This is a function for the variable x is equal to U, and this one here is the function for y. In this case, I put a probabilistic function here that is probability of x given x and u, P of y given x u, and whatever numbers are these numbers here. Now, from this fully specified model, we can compute these two different distributions that we're talking about. That's the one that we were using before. The distribution in this distribution here is the one that is coming. This distribution here is the distribution is coming from the data that shows that E of y given x1 is greater than E of y given x0. On the other hand, we don't have access to that, but this is the distribution in the right, the one that if I do the intervention in the system, the do distribution. In this case, is the flipped. The E of y given do x0 is greater than the E of y given do x1. Layer 1, L1, and L2 is just about the layers of the hierarchy. This is experimental layer, this is observation. Now, if you don't have access to this guy, because this is what we're trying to learn, and we just have access to the data that is coming from here, from this line here, it seems that x is equal to 1 is looking quite good. This is a joke. Should I do it in the causality? Because it looks good. It looks good based on the data. Now, for sure, the answer is like it's catastrophic if you do it based on based on what I just showed you, the plot. The answer is no. It's quite misleading that this is happening. Then this seems to suggest that you should just throw away the data and start from scratch, which is completely unsatisfactory answer. It's like a tragedy, because it would mean, this would imply that any agent in the world should always throw away the data if it was not collected by him or her, and should just start learning from scratch, which, yeah. Now, reasonable questions here. How do I know that this pattern that I just showed is not present in my data or my environment, I should say? We don't know, we never know. That's the truth. That's why I'm calling attention and screening here. Number two, does this then imply that I should throw away all the data not collected by me, the agent in this case, and should just start learning from scratch? Hopefully not. This is, it's kind of throw away history and communication and everything that we would have. After all, is there any useful information in the observational data? And the answer is yes. It is not perfect. That's the realization here. But there is something there that is still capturing aspects of the underlying SCMM. Now, let's try to understand and leverage this kind of what's called the confounding data. And I'll just go quickly here because I may have more minutes, but I want to leave maybe 5 minutes for questions. I'll try. To be very simple approach, the details will be the complicated, but the general idea is very simple. We will try to extract causal information from the confounding through the idea of doing bounding. In other words, I will not try to do a point identification, get exactly what is the y given to x from the p of x and y, the non-experimental data, but I will just try to put bounds over this quantity. It turns out, and I will not go over it, there's theorems about how to do that. Then I can get a lower and an upper bound there. This is started, there are ways of doing that depending on the setting. This is started from Balki and Pro in 1996. After, I would say 10, but 20 years, there's more results coming from this Ichkai paper in 17. This is still non-parametric. There is ideas about how to incorporate some type of parametric knowledge by Carlos and Zhu in 18 and so on. And there is an interesting case that I'll try to mention later about when you have sequential settings, that is kind of generalization of MDP in this New Rips paper, and ICML them. But anyhow, there is ways of doing this type of bounding here in a relatively general way. Now, the second step would be, now that I have bounds, I will not set as a prior, but I will just do some type of, don't need to parse for someone that asked about the Thompson sampling, but the idea is just, instead of just sampling from the underlying distribution and picking the highest one, I will just do some kind of rejection sampling. That very simple idea. I just do some type of rejection sampling here and try to enforce the bounds that we just got from step number one. Now the question for us is like, if you do that, again, I'm just give you the high view here, high level view. If I do that, what happens? Results are kind of amazing, at least in my opinion. That is like, this was the kind of catastrophic situation. Then if you use the data, comparing about discarding the data, it seems that we are in this bad situation and you should discard. Now, if you use, which is bad, going with the blue. If you use the data in the proper way, and the proper way is like the papers that I mentioned before, we get this kind of green behavior here. That is, I call clever observational data, because there is information in the observational data about the causal effect. Note here, just if you want to zoom in what's happening inside the algorithm, note here that this overlapping that we have in the beginning, that I need to do experimentation on this trial and error to try to remove the overlap between the do x0 with the do x1. This is already, there is a lot of mass chopped here in this beginning that is coming from the observational data. Then this is in reality an easy task for the particular setting that we run the simulations. I didn't give the details here I forgot, it's in my notes, but anyhow, you can drop me a line about the experimental setup. The idea is more important. But anyhow, the performance improvements by order of magnitude in practice, which can be proven in very general settings, and those are the references. Now, the summary here, I'm not reading the questions, by the way, the things in the chat. I'll read later. Someone can help me later with the question. I see that something is popping up there. The big picture here, the summary, what I just said, the generalized policy learning, the idea is like we have a causal graph, we have the graph under the do intervention. Now I have observations collected. This is data, that OBS, that is collected in the left. What I'm trying to do, I will do some kind of causal bounds in order to learn this U of y given to x, where x is picked by the policy pi. And the bounds will be the one guiding this process. But this, and in other words, yeah, that's it. We need to go online. We just want to go online in a more principled way. Then this is why I call it the generalized policy, because we are kind of mixing the online and the offline type of mode. In case you cannot do this entirely offline, or just do the planning entirely in the mind of the agent. That is a kind of new, I would say for me, a new modality. Happy to hear your thoughts. Now, just a quick note here before I go, because I'm over the time and I want these questions. The DTR, I just want to mention that you can do something that is called the DTR, that is some generalized MDP, that is called dynamic treatment regimes, very used in the medical domain when you have multiple axes, multiple states S, and there is a latent variable affecting essentially everyone. And it's quite challenging setting, and still you can do the same kind of results. And this is the randomized, how it's found in the literature. If we use the DTR, new randomization that you have taken into account this structure, this is what you get. If you use observational data, that is the green, the problem is essentially a trivial problem. Then anyhow, I think it's quite cool if you are in the MDP, POMDP business. For details, this is in these papers. Now, conclusions. Causal inference and RL are fundamentally intertwined. And novel learning opportunities emerge when this connection is fully understood. In practice, failure to acknowledge distinct features of causality almost always leads to poor decision making. The goal here, or the program that we're engaged in, is to develop a principal causal AI framework that integrates observational, experimental, and counterfactual data, modes of reasoning, and knowledge. This leads to a natural treatment of human-like explainability, and what I like to call is a good discussion. This is more for the beer or the whiskey, the rational decision-making, or what rationality means here. So no joke, it's a good question. His sources, I already shared this one. Thank you very much, and happy to take the questions, or some questions.